All right. So I do have a warm-up for you guys. We did partial derivatives, tangent planes. What else did we do? Chain rule. That's where we left off, I believe. Chain rule, right? Today we're going to talk about two things. One called the directional derivative, and something that we're going to use for the rest of the semester called the gradient vector. Okay? So here's my warm-up for you guys. Let's see here. So let's say if you are standing on a point, let's say the point is 1, 1 on the xy plane. Not if, it just says you are standing. Sorry. You are standing on the point 1, 1 on the xy plane, period. So what I would like you to do is create a vector that points in the direction at which x increases and leaves y constant. There could be more than one answer. So just think about you're on the point 1, 1 on the xy plane. I would like you to create a vector that points in the direction at which x is going to increase, but it'll leave y constant. And then just with your groups, your usual groups, just kind of share your vector, see if they agree that that vector satisfies the criteria. If not, maybe kind of give some feedback. As you guys do that, I'm going to pass back some homework. I think you guys usually chat. You two here can chat. Okay. Kevin, Ben, you guys. Cross here. We have you two chat here. I have you guys chat here. Then I have here and. All right, and then I'll have you guys chat as usual, and then you guys can check in here as usual. All right, so create a vector. You're not sure where to start. Maybe see how your classmate's starting. Lighthearted question. It's a lighthearted question. Not a trick question, guys. Something to get us started. We'll just start right? Jake changed tab. All right, guys, let's see. Saw some vectors on your papers here. Clint is no longer here. Eleni, can you share what you your group came up with? Just share the vector here that you came up with.
And the vector is x comma 1. So
X comma 1 like this?
yes.
Cool, okay. X here meaning like it could be anything?
Yeah.
Okay, all right, cool, thank you. All right, let's see. Lucas, what did you guys come up with? Thank you.
This whole idea that x comma 0 because the y has to not change.
Okay, so you're a little similar, but you just said 0 instead of 1. Okay, thank you. Beth.
We just did the x comma 0.
Also this one? All right. Let me add one more here to my list. Kevin, oh wait, you guys are in the same group. Okay, let's see. 7.
Beyond that.
Which one?
No, it's the.
Okay. Any other vector that I can add to this list? Ethan, yeah.
Wait, you can't just say x, because x would be negative.
Okay. So we can't just say this because it could be negative. So you want to maybe add like a little restriction to it?
Yeah, I'd say x comma 0, but x has to be positive.
Okay. Or x is positive. All right. Thank you. Sam? Okay, so you're saying I could just do that instead. Cool. Yeah.
Also specify that x will be there.
And also specify that x can be 0. So let's say maybe for both of these, right? No one has to be 0. Okay? How does that look so far? So x cannot be 0. X cannot be 0. Okay? So let's see if you're at the point 1, 1, right? So if we're at the point 1, 1, 1, 1, and you're gonna make a vector from there, right? What's the initial point of that vector? It's gonna be 1, 1. So that's the initial point. So then you guys are saying, let's see, we had something like this, okay? So give me a value for x. Let's make it negative as well. -2, okay, so let's say we got -2, 1. So this is important. Remember that means that you're starting at this point, but what does the -2 tell you to do from there? You would go back 2 in the x direction. So you would go 1, 2, and then what does that tell you to do? Go up 1 in the y direction. So then that would be a vector that points up there, right? And so I'm guessing the reason you guys were saying this would be 0 is because you don't want the y to change in this case. If this was negative, why does this not agree with what's written on the board here? X is not increasing, right? This has x value +1, but this now has x value -1. And so x decreased. Okay. So yeah, so you guys are right. You want x to be positive. That way you're always going to force x to get bigger. And because you're going to have y equals 0, so instead, if I do this, let's say it's +2, then we would have 1, 2, x would go 1, 2 units over, but then y doesn't change at all. So then you would end up with this vector, where that has 2, 3. And notice that y stayed constant visually. Okay? All right. Great. So that's kind of the theme of what we're doing today, is using vectors to point us in certain directions that we're looking for. Keep in mind everything that we just discussed here, and visually everything that was discussed here. Okay? All right. So I think we're ready. Let's see. So section 14.6. What's up? 14.6. We're going to start with something called the directional derivative. Let's do a quick recap of what we already do know. So let's see. So we've seen how for a function z equals f of xy, we defined the partial derivative with respect to x. What did this output? What did it represent, Jacob?
The change, rate change the function in the x direction.
In the x direction, right? And so we wrote that with partial change of z with respect to the x direction. And so yes, now let me write that in words. So the rate of how z changes with respect to x. And then similarly for the partial with respect to y, that's going to be our rate of how z changes, but with respect to y. Rate of how z changes with respect to y. Make sure it's recording. Yeah. Okay, so let me wait for you guys. Again, we're at this point, okay, from the warm-up. We're at this point. Can you guys give me a unit vector so that I'm gonna change with respect to x only and leaving y constant? Can you give me a unit vector? Let me hear from this side of the room. Think about it. Remember, you want it to be a unit vector. All right, check in real quick, check in. So check with your classmates, see if you guys can think of a unit vector so that only x is increasing and y is not changing. Okay? I still want to hear from this side of the room. Any vectors? Any unit vectors?
1, 0.
1, 0? Okay. So notice 1, 0, right? If we did 1, 0, that vector would go here. X only increases by 1. Y stays constant. So what is the magnitude of the vector 1, 0? 1. What's the name though? Remember we gave it a name. I hat. Exactly. So what I want you guys to notice is that when you're doing this motion, so this moves in the direction of I hat. All right, so if I'm standing on that point, if I move in the direction of I hat, that's the motion that's being represented with that partial derivative. Jacob, question?
Can I do my homework? I just got here.
Oh, yeah, sure. I hat, which is the vector that changes x by 1, but leaves y, does not change y. So what direction of motion is the partial derivative with respect to y?
J hat.
It would be j hat, where you leave x constant, but only y is, sorry, x constant, but y is going to increase. So it moves in the direction of j hat, which is the vector 0, 1. So let me show you a visual. I have a hell of visuals today, so I had to actually print them out. So grab one, pass it back. Let's give you guys a stack. That will be helpful for today. Grab one, pass it back. Grab one, pass it back. No, here you go, bud. Grab one, pass it back. So we're going to look at the visual on top. Oh yeah, grab one, pass it back. It's all good. So let me show you, let's do a quick visual of kind of what's going to happen. So this is only giving me the rate of how z changes with respect to those two directions, right? So now what we're going to do is, what if I want to see how z changes with other directions, with respect to other directions? So if you guys look at the visual on top, let me open this up. Turn off my light. Let me open this guy up. Make sure that's on the recording. Okay, so here's the game plan. We're gonna have a point on our surface with coordinates x naught, y naught, and z naught. And right above the point x naught, y naught, which is on the xy plane, okay? At that point, if we move in the direction of I hat, so if we move in the direction as x increases, that was giving you the partial derivative with respect to x. As you're moving in the direction as x increases. J hat was moving in the direction as y increases. So those are the two directions. But now what we're going to do is, what if I want to walk in a different direction? And that direction will be told to you by a unit vector u. Okay, so imagine I'm a point, I'm on top of a point, and then the u vector is going to help me, it's going to navigate me to where I need to go. And so the game plan is, I want to look at the rate of change from going to this point to some other point on the surface, but in the direction of u. That's kind of the game plan. That's usually what's going to end up happening. So refer to that visual when we're doing this next part. So let's see how we're going to do this with all the math stuff. Stop sharing. All right, so let's see what's up. So here's the goal. Find the rate of how z changes as we move in the direction of some unit vector, and we're going to call it u, on the xy plane. Okay? And so now refer to that visual that's on the top of your page. So let's consider a point P which has coordinates x naught, y naught, and z naught on the surface of F. And let's let u, and let's give it components. We're going to call the components A and B, be a unit vector with initial point x naught, y naught, which uses the x and the y naughts from the point on the surface. So it's like this 0.11 here. Ah. All right, so let's look at a picture real quick. What's happening on the xy plane? So again, refer to that picture that's on top, but here we're going to do a big zoomed out version of what's happening on the xy plane. So you have, let's say x naught is right here, and let's say y naught is right here, and then you have this point right there, x naught, y naught. Okay? And you guys see that point Q that it's referring to on the top of the surface? It's kind of like a little bit in front. So this point here refers to the point P that's on top of the surface. And then let's say point Q is over here somewhere. And so we have this vector here. We have this vector here, so that this vector here is pointing in the direction. This is the unit vector. Sorry, this is not u here. This is not u here. Let's say u is somewhere here. Sorry, q. Let's say q is somewhere there. But the unit vector, I'm making it hella big, okay? Because we're zoomed in. The unit vector is pointing in that direction that q is, that you're pointing towards q. Okay? And the tip of this bad boy, shit's aligned. If the x coordinate is x naught, but the x component of vector u is a, what would be this x value where vector u ends?
X naught plus A.
It'd be x naught plus a, just the way that you guys were doing the vector. From here, you were just adding whatever the x component was to the x value of that point, right? Similar thing we were doing, but here we're doing, we don't have actual numbers. So it's going to be whatever this x value is plus a. If this is y naught, what is the y value at the end of that vector? If this is the y component of u, y naught plus b. But here's what we're going to do. If you guys see that picture, we're going to do a scalar multiple of u so that we make it smaller. And we're going to multiply it by the scalar h. So then this bad boy here, this vector from here to here, that's going to be vector h times u. It's scaling it down. It's making it a little smaller. What is h times u going to look like? What are the components going to look like? HA and HB. So then the x component here is still going to be x naught plus now, but now I'm multiplying it by h, I'm adding it by HA. And then here it's y naught, but now it's being added by HB. So that's like the zoomed in version of what's happening on the xy plane. And so it's hard to do this with on the picture here, but this point is the one that's on P on your surface on the picture, and this is the point Q that's on your picture. Okay? To make this point get closer to point P, what do we have to do to H? Increase it. Do we want H to get bigger or smaller if we're trying to get these points closer together? We want them to get smaller, right? So that's now kind of where the limit's coming in. And so here's the goal. This is what we're going to want to do. Is to find the rate of how z changes as we let h go to 0. Okay? As we let h go to 0. So let's see how we're going to do that. So notice that there's a limit involved. Yep, okay. So this is how we're going to define what's called a directional derivative. We're going to say the directional derivative of f at the point x naught, y naught in the direction of a unit vector u with component AB is, and now instead of saying f partial of x or f partial of y, it's u. Okay. It's the vector u that's telling you which way to go. So we're going to write it f with respect to u though, with the vector u. Okay? At the point x naught, y naught. Here's another way your textbook writes it. They write large D for, it stands for an operator, which we're not going to get into, but think of it as just the derivative with respect to u of the function f naught, f of x naught, y naught. This is the way the textbook will write it, but you can also write it like that. You use both. Sure.
Is h and u a scalar? So is q always the end of the vector?
Correct. Q will always be the end of the vector HU. Yeah. Because u is a unit vector. It's going to stay that length. It's this vector HU that's going to be changing magnitude. Yeah. Okay, good point. Okay, so this is how we're going to do it. You guys look at your picture. The point the point above this bad boy, P, and then the point Q. Let me actually write the coordinates so you guys can see it here. X naught plus HA, Y naught plus HB, X naught, 1. We're going to look at the difference of the Z values at those points. So we're going to have to plug them into the function f to get their Z values. Right, so the output value of this Z value minus the output value of that, we're going to write that here. So f of X naught plus HA, comma, Y naught plus HB, minus f of X naught, Y naught. Those are those Z values corresponding to the points on the surface that you guys have in your picture. So this is the change in the Z values. But now we want to say with respect to the distance of these 2 points. With respect to the distance between these 2 points. Okay? How would you find the distance between these 2 points?
J squared, the square root of HA squared plus HB squared.
How can you use the vector to find the distance between those 2 points? Notice that the distance, right? So the distance from P to Q is the magnitude of this vector here, right? It's the magnitude of the vector HU. And we saw a scalar multiplication property that says that's just the absolute value of H times the magnitude of U. But what's the magnitude of U? It's just going to be 1 because it's a unit vector. And this is why you need it to be a unit vector. Right? So that distance between those is H. Because we're going to have H be a positive value. So that's just H. That's why we need that unit vector. So then the distance between the 2 points is just going to be H. And then that's why you'll see that in the formula. So this is the change in Z values with respect to the distance between the points given by these two coordinates, X naught, Y naught, and sorry for making you write all this. Jesus. Welcome to Calc 3. Cool. Questions? Anything you want me to repeat? Jacob, yeah.
So are you just taking the limit?
Oh, thank you. Hello. The limit, yeah, and then we're going to take the limit as H goes to 0. Thank you, Jacob. Yeah. Okay. What does that do on the picture? It's going to make those 2 points get smaller, closer and closer together. Let's see. Okay, so this is the definition here. I'm going to draw another picture here. I feel like I'm squishing too much stuff here. Okay, let's just focus on the vector HU. So draw another picture here, and just focus on this bad boy here. This is at X naught. This is at X naught plus HB. This is at Y naught. This is at Y naught plus HB. So this is HA. Okay, we're just focusing on this part, okay? So from here to here, notice that this distance here is the change in the Y coordinates. We're going to call that delta Y, okay? And from here to here, this is the change in the X coordinates. So we're going to call that delta H. So this is what I want you guys to notice, which we're going to use in a bit. Notice the following. We got vector HU, which, as you guys told me, has components HA and HB. If I'm at X naught, right, how much did we increase this x value to this x value? How much distance was increased from here to here? HA, right? So notice that HA is really just that change in x. How much did the y increase to go from here to here? HB. So notice that HB is just that distance delta y. So if we say that we know that this is x naught plus HA, if this is just some arbitrary point xy, right? Which, yes, right now it's this guy and it's this guy, but let's just say it's some arbitrary point xy, and this is x naught, y naught. Then the way we would compute that change of delta x is we would subtract this x coordinate with this x coordinate, the way you've kind of been doing it since Calc 1. So this is just the change in x with this arbitrary x value here that might change depending on what h is, because that's the thing that's varying. And the change in y is that arbitrary y value minus that fixed y value. So here's where this gets kind of a little bit lost in the textbook. These three things, HA, delta x, and x minus x naught, those all represent the same thing. We're just writing them in different ways. HB, delta y, y minus y naught, will also represent the same thing. So I know you guys don't want to take a derivative using limits, because as you guys saw, taking limits is pretty gnarly from section 14.2. Or it can get pretty gnarly. So if there's a way that maybe I can use derivatives to help me compute this, then that would be the dream. All right, that'd be dope. So if you guys look at your picture, take a look at your picture. Look at point P. It's not shown here, okay, but in section 14.4, when we did linear approximation, there's a tangent plane that touches that point P. So we're going to use linear approximation here in this next piece, okay? So imagine there's a tangent point at that point P. So consider the tangent plane at that point, x naught, y naught. And instead of z naught, I'm just going to call it the output of the function, like that. Okay. From section 14.4, we saw that the equation of the tangent plane is given by z equals, let's see if you guys review it a little bit. If there's a surface of a function, and then these are the coordinates of a point on the surface, what did the equation of the plane end up being?
fx naught, y naught.
Fx naught, y naught.
And plus fx, and then x minus 0.
Fx at what point though?
X naught, y naught.
Y naught. And then x minus
x naught.
x naught. And then there was the
fy.
fy part, right? Good. All right, that's the equation of that tangent plane that's going to touch that point P right there. Point Q doesn't look like it's that close to it on that picture, but as h gets smaller and smaller and smaller, that point Q is getting closer to point P, right? And then therefore, on the xy plane, this point is going to get closer to this point. Okay? So by linearization that we talked about in that section, as h gets smaller and smaller and smaller, it's going to force point Q and point P to get closer together. So we have that the point Q, which let's just say has points x, x and y, gets closer to point P, which has fixed coordinates x naught, y. And since right now we're actually saying that point Q has x naught plus HA, y naught plus HB, right by this picture here, x coordinate is x naught HA, what coordinate is that? That means that if we plug in those coordinates into my function, which are very close to our fixed point, remember that we said through the linearization, that output value of that point on that function, since it's very close to the point x naught, y naught, as h gets smaller, is going to be approximately what you get when you plug it into the equation of the tangent point. Okay? It's going to be approximately what you get when you plug in this point into this x. Sorry. Yeah, into this x, into that y. Yeah, no, a circular way. So you're going to plug in this bad boy into this x, you're going to plug in this bad boy into this y to give you an approximation. So it's going to be f of x naught, y naught, f partial with respect to x of x naught, y naught. Okay, and then here's where I need you guys to help me. What's going to be this x coordinate minus x naught? HA, right? Because remember, x minus x naught is just HA. Okay? So that's HA. And then we got, now we're going to plug in the y coordinate of that point into this bad boy. And that's going to give me what? It's going to give you HB. And so, do you guys see how this guy is this one in the limit definition? And this one is this one in the limit definition. So let's subtract both sides by f of x naught. So let's do this. F of x naught HA, y naught HB, minus f of x naught. If I just subtract this to this side, is approximately equal to x naught, y naught times HA plus f partial of y, x naught, y naught, HB. Okay? And as h gets getting smaller, smaller, and smaller, that means that these two start to become equal to each other as h keeps getting smaller and smaller and smaller. So from here, we have that the limit, or actually let's do this. Okay, this is where we're at. The limit as h goes to 0 of x naught plus HA, y naught plus HB, minus f of x naught, y naught over h. That limit as h goes to 0, well, this numerator becomes this expression here. Because those points are just going to keep getting closer and closer and closer together. So the limits are going to be equal to each other. So then I can replace this numerator by this expression that it's approximately equal to here, as the limit as h goes to 0. HA, partial y, x naught, y naught, HB over h. So what can we do from there? We can cancel that h out. Get that full out of there. Later, bro. We factor it out, cancel. So we end up with the limit as h goes to 0 of f partial of x, x naught, y naught times a, plus partial of y times b. Are there any h's though? There's no h's, so what is the limit going to equal?
Equal to that expression.
It'll just be equal to that expression. X naught y naught a partial y x naught y naught b. And so since that limit is just going to end up being equal to this bad boy, we end up getting a nice little theorem here. It says if our function is differentiable, if f is differentiable, then for any unit vector u, which has components a and b, its directional derivative with respect to u at any of those points is just going to be equal to the partial derivative with respect to x times the x component of my unit vector plus the partial derivative with respect to y times my y component of my unit vector. And by doing this, using this theorem, we can now just take partials to help us find the direction and derivative instead of that whole nasty limit stuff. Jacob.
I guess you could just also express it as the dot product of the unit vector.
We're getting there. Almost there. Almost there. Yeah, we're almost there. We're almost there. Yes, the dot product will show up. Will creep up in a little bit. We'll creep up in a little bit. Write this down. All right. Give me 1 second. Okay, so let me show you again. We just did hella like theory here. So any question on a particular step? So this is just kind of like a mini proof of explaining this theorem, okay? Because it's kind of surprising if we just wrote it down. It takes a little bit of convincing why that needs to happen, okay? So when we find the directional derivative, this is how it's defined. But on the homework, you're going to have to end up taking partials with respect to x and y to actually compute, okay? Again, let me remind you though, what the hell's happening? There's a different visual here. I think I'll leave it. So let me give you a different visual from your picture. Okay, so here's my surface. Nope, yeah, let me turn off the lights. Here's my surface. And what I want you guys to remember is the unit vector u lives on the xy plane. It's on the bottom. It's here on the xy plane, okay? And you're on the surface. Imagine you're looking below though, and you see the unit vector and it's pointing in this direction. So that's telling you to move towards in the direction of u. So then your points are moving in that way, in that direction. Right? So I'm here at this point. I'm going to start moving towards that direction. So notice that z in this particular surface is going to increase. Okay? But if I have a different vector, if u is pointing in a different direction, now I'm going to look below me and I'm going to see u and notice that it's pointing in this direction. So now I'm going to walk up the surface in that direction. Again, z is increasing from this picture, this particular scenario. But let's say now u is pointing towards the origin on the xy plane, okay? Now if I walk from that point P towards u, now what is z doing? It's decreasing. So what kind of value are you going to get? What kind of number will you get for your directional derivative? You're going to get a negative because z would be decreasing. If u was a different vector pointing in this way, then what would be the answer to your directional derivative? Positive, because now you're going to be going up the surface. That's visually what's happening. So what you will need to do is either you're going to be given the vector u, or you have to find the unit vector u to then help you dictate which direction you want. Okay? And then we're going to do all this stuff here to figure out the actual rate at which z is changing instantaneously. So what I want you guys to notice, going back to the warm-up, okay? U has to be a unit vector. So what I want you guys to notice is if u is the unit vector I hat, if u is the unit vector I hat, which has components 1 and 0, then your directional derivative, what would you end up getting using this theorem? You just get the partial derivative with respect to x, because that is what you've been doing. You've been changing with respect to x increasing lambda. So notice that the directional derivative in this case is just the partial derivative with respect to x. But if your unit vector is j hat, which has components 0, 1, then now your directional derivative is f partial of y only. Right, this is 0, so that goes away. This is 1, so it's partial of y. So we've been doing two instances of a directional derivative, only those two, I hat and j hat. Okay, what time is it? All right, very theoretical, very lecture heavy, sorry. Let's look at some concrete examples, and I'm going to have you play with some, so you guys can kind of try to see how to put this together. All right, let's check it out. So this is what you'll see in your homework, okay? Let's look at this example here. So let's get a function. So for the function, let's say negative x squared minus y squared is 2x plus 6y. Big old polynomial. We're going to do two problems. Let's find the rate of change at the point P, which has coordinates 1, 1, going in the direction of Q, which has points 0, 0. Now the homework won't say find the rate of change. They're just going to say find the direction of the derivative. But I want you guys to remember it's a rate at which z is changing, or the output is changing. So we try to use this theorem. Let's just do a little strategy plan here. What are the things that we need? We need the partials. We definitely need the partials. What else do we need? We need the unit vector AB. So we don't have a vector. Just tell me the direction, but I don't have an actual vector, unit vector. So let's do a little picture first. So let's just kind of see what the heck's happening. So I got 1, 1. This is my point P right here. And my point Q is the origin, right? And so I'm going in this direction like this. So what do you think we have to do? You guys help me out here. We'll do the partials in a little bit. We need the vector, right? So how would I start doing it? How would I start doing it? Say it again? Yeah, we're going to find the vector PQ so that it points in that direction and it starts here. Okay? So notice the vector PQ. Help me out here. It would be what? 0 minus 1. Remember, it's terminal minus initial. 0 minus 1. 0 minus 1. Okay. Is this my A and my B that I'm going to end up using? I see some yes and I see some no's. The no's, why is it no?
It's not a unit vector.
It's not a unit vector. It's not a unit vector. Remember, you need it to be a unit vector. So what do we got to do?
Divide by the magnitude.
Divide by the magnitude. Perfect. So let's let U be PQ divided by its magnitude. So that's going to be -1 divided by, what is that? Square that, add it, so it's √2. So then vector U is just -1 √2, -1 √2. Okay, so I got my vector U. From here, what are we going to do?
On the partial derivatives.
On the partial derivatives. All right. Find the partial derivatives. Help me out here. -2x. What's that? 0, 2, 0. 0. 2 and 0. And then let's see. Let's find the partial with respect to y over here. So that's going to be what? 0 to y 6. And then what do we have to do with those partials? So remember that we're going to want to plug in, we're trying to find the directional derivative at the point, right? Where is the coordinates of the point? Here's where you got to be careful. Yeah. The question is do I use this point or do I use this point? Use P. Yeah, it says at. That's how you know which one you're plugging in. You're starting at this point and then that's you move from there, okay? So then you're going to want to plug in that point at these partials to give you those values. Let's see, that's going to be, is that -2? Or am I tripping? 0. Is that right? And then here you plug in 1, 1. What's that going to give you? 4. And so then now we put everything together. So the directional derivative at the point 1, 1 is the partial of x at 1, 1 times a, which in this case, this is a, this is b, -1 √2, partial with respect to y at 1, 1, b is -1 √2. So then you go ahead and you plug in these values that you found. This is 0, 2, and then this is 4. All right, help me out here. So what do we end up getting? Negative, say it again? 4 over √2, and I think you guys rationalized it, right? Okay, you can rationalize it. I helped you out here with the decimal, so in decimal, this is approximately -2.8. So what's happening on the surface at point P as you go towards Q? C is decreasing approximately how many values? 2.8 units. All right, here, I want you guys to try one. So find the rate at P11 going towards the rate of change going towards the point R, which is 2,3. Yeah, there's problem 2 using the same function. Yeah, thank you for asking. Try it out. Check with your host. All right, guys, so just real quick, stop what you're doing, check in with your group, and then just see if you're kind of on the right path. Maybe share with them your strategy you have so far. Just do a quick little check. Yes. I'll go around, let me know if you have questions. So what's happening? Keep working, guys. I'm just gonna post some important things that hopefully you have.
Sorry, Professor. Earlier, I wanted to point out that I had like a whole bunch of extra copies.
Okay.
So yeah, sorry about that.
It's all good, bro.
Yeah, so want to find the unit vector.
All right. So hopefully this is the unit vector that you ended up getting. You want to go towards PR, but you want it to be a unit vector. Don't forget that unit part. That can get you, okay? Let's see. Same partials. So it's going to be the same partials that we did here, that we got here. But now you're going to plug in those partials at the point. Which point are we plugging in?
1, 1.
It's still 1, 1. It's just that the unit vector is the one that's different. And so that means that when you plug in 1, 1, it's still going to be the same values as what you got here. So it's still this bad boy, except that now it's being multiplied by this. This is the new A. This is the new B. 1/5. And then it's still this partial at 1, 1. And 2/5. So this is going to be 0. So what you guys end up getting here? 8 over root 5. Some people were rationalizing it. 8 root 5 over 5. And that's going to be approximately 3.6. 3.6. So what's happening on the surface above that point as you walk in the direction of R? What's steeper, going that direction or going this direction? What do you guys think? Which one's steeper? If I go towards Q, is this steeper going down or is this steeper going up towards R? R is steeper, right? The rate of change of Z is a lot bigger than how it's decreasing. Beautiful. Good job. Okay. So, again, let's see what the hell we just did. Stay. Okay, so let's see. So let's see what's happening here. Stop moving. Okay, so we got, this is the surface of this function, okay? Here's the point P at the point 1, 1, right here. As you went towards Q, which was the origin, look, notice that it's indeed going down. It's going downhill. Right, here's P, and then if I go towards Q, towards the origin, let's see if you guys can see it from this angle. It's going to force the points to go down. So yes, you are going down. But if you're here at 1, 1, and you go towards R, what was the coordinates of R again? 2, 3. So that's going to be towards this direction. Notice that it definitely is going up as you walk in that direction. Okay? Sweet. All right, so let's see. So, all right. Jacob earlier said that there's something like a dot product. So let's see what's going on. Let's see. I think what was trying to say with that. Oh, he's done for a little break. Before we get there, this is my unit vector U, which has components 1 to 5, and this is my vector. Someone with a calculator, help me out. What would be the components here in decimal form? 0. What? 707. This is 0.7. 0.7. Okay, and then this is, help me out here with this one. 0.4. So this one probably 0.8-ish. 0.9. Okay, let's say 0.9. All right. You guys are getting a little tired, so get up. Stay where you're at. Get up. Stand up, stand up. Okay. You're at a point. You're at a point on the XY plane. Okay? What I would like you to do, right here, this is the x-axis. This is the x-axis going this way. This is the y-axis going that way. Okay? I want you to rotate to a vector in this direction so that x will decrease by -7 and y will decrease by -7. Positive x-axis, positive y-axis. So I want you guys to figure out which direction should you look at so that x is decreasing by 0.7 and y is decreasing by 0.7. Okay. Okay, so look at the room. You guys see how you're all facing in the same direction? Well, you can't. If you're in the front, you can't. But if you're in the back, everybody's pointing this way. Everybody's pointing that way, okay? Now I want you to move your body so that you're pointing in the direction of this vector, where x increases by 0.4 and y increases by 0.9. All right. You guys see how everybody's pointing in the same direction? Kind of, relatively-ish. Okay? That's the direction dictated by you. Okay? And then what I want you guys to notice is you're all facing that direction. That's what's important. Okay, you can sit down. We're going to do this again after the break. But then I want you guys to notice there's gonna be a difference. You won't all be facing in the same direction. Okay? All right. So let's see. Let's talk about this property here that you guys were noticing. So let's take a closer look. At the theorem that we were just discussing here. Okay, let me say the theorem. All right, so the theorem tells us that this directional derivative at this point is f partial of x times a, which is the x component of my unit vector, and f partial of y of b. And so notice this is a product of two things plus the product of two other things. Okay, so it looks like it's two vectors. I can rewrite it so that it's a dot product of two different vectors. Okay, what do you guys think this vector's components would be? F sub x at xy and f sub y at xy. And what do you, if that's the components of this vector, what would be the components of this vector? AB. Okay. This AB vector is your u vector. And so that's this vector here, dotted with your u vector. And so I can kind of think of this directional derivative as the dot product of these two vectors. The question is, what is this? What is that vector? We've seen partials, but we haven't seen that vector. Okay. So this is a new thing, a new object that came out of life from this theorem. And it has a special name because we're going to see throughout the rest of this class. It's very important. Okay. This is what we're going to call the gradient vector of f. And it's going to tell us hella information. And the notation that we're going to use, it has a special notation for it since it's so important, is the word, when you see the word gradient, you're going to see this upside down triangle, and you're going to read it as the gradient of f at that point, xy. Dotted with my unit vector. So instead of writing it like this, this is the new notation here that we're using for that. In LaTeX, so you guys, you have to LaTeX this. This is del. Okay, and it'll give you guys that the gradient, or the other way. Do you guys want an example and then a break, or do you want a break and then an example? All right. Example. All right. So let's see. So actually, hold on. Let me. Yeah. It's no. I'll leave that one. Okay. So let's see. What is this? What is that vector? Like, that's such a funky thing that just came out. How many coordinates does this vector have? So it lives on the XY plane. Same plane that U lives in. Okay? Don't forget that. Okay, so let's see. Let's see what the relationship is between the vector U and this new vector here. Let's explore that with this example. So let's use the same function. Negative x squared minus y squared plus 2x plus y. Let's look at what the gradient vector at the point 1, 1 is, and the unit vector that you guys did for this example. 1√5 and 2√5. 2√5? 2. So let's see. We already know the components of this bad boy. By definition, this vector here, what we have to do is use the partials and plug in that point here. So when you guys are asked to find this gradient vector, what you need to do is take the partials of the function and plug in that point. Okay. And I believe the partial of x we said was negative 2x plus 2, and the partial of y was minus 2y plus 6. So then what would be the components at 1, 1? 0, comma 4. Okay. If I sketch this bad boy out, let's see, we got go like this. I need you guys to make this a little big on your notebook, okay? It's gonna be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7. 1, 2, 3, 4, 5. And then 1, 2, 3. Okay. So our point P is still, or our point is still at 1, 1. So it's still this bad boy right here. It's still this point, 1, 1. And here's how you want to think about this gradient vector. You're gonna again start at the point 1, 1, and you're gonna draw a vector, the gradient vector, with that as your initial point. Okay. So how do I draw that vector starting from here? How much does x change? What does y do? It goes 4 units up, right? So 1, 2, 3, 4. So it goes right here. So this vector right here is the gradient at that point 1, 1. Now let's draw the unit vector at that point, where I was having you guys rotate, remember? We said that that vector has approximately, this is approximately 0.4 and 0.9. So starting here, increase it by about 0.4, and then y increases by about 0.9. Do you guys see how that's going to be this little bad boy right here? Is that cool? Okay. That's u. Okay? It's small because it's a unit vector. This is definitely not a unit vector. Okay, so this is what I want you guys to do for this visual here. So now I want you to do it at other points. And I want you to sketch the gradient vector. But now I'm going to put another point, negative 2, comma 5. Sketch that vector. And the same vector u. But I want you to sketch it at this point. And then do the gradient of f at the point 4, 8. And at u. And u as well. So you're going to do negative 2, comma 5. Do what we did here. Sketch the gradient and sketch u, with this being the initial point. And then do it for the point 4, comma 8. Oh shit, come on. Negative 1, negative 1. Negative 1, negative 1. So then what you do. So find the gradient vector at this point, and then at this point. And then when you sketch your gradient, start from that point. And then just compare your pictures, see if you have a similar visual as your classmates. Remember, how did we find this gradient vector? I had to plug in that point into the partial derivatives to find the x component and the y component. Okay? So try it out. Go around, help you out. All right, guys, check each other's work real quick. I do see some different pictures. Check each other's work. What's going on?
Yeah.
Okay, so for number one, you want to instead of plugging in that one, you're plugging -2.5 into this portion. So what would you get? Use the same unit. Guys, use the same vector, okay? Use still, that guy does not change. This guy's not changing. I still want you to use the same U. Still the same U. Exactly. So when you're reverse that line. -4. Then plugging that point again, but now into this different pressure. So go ahead and do that, okay? So then write it as well. So that would be so from this point, you're going to draw that vector 6, -4. So you're going to go 6 in the x direction, 4 in the y direction, and then sketch that. All right, guys, so we are going to go on a break, but as I told you, I'm being evaluated. Got my boy Mohan over here. He's gonna grill me. Can't wait. Real quick, guys, real quick. Eyes up here. So we're gonna go on a break, but Professor Mohan's gonna give you guys a little information about the student evaluations that I told you about. Then when you're done, you can go on your break. I have to leave the room because I know you're gonna like say hella shit about me. So I don't want to hear it. I'll just leave. But we'll resume at 2:20. Okay? So we'll resume at 2:20. And let me pause the video. All right. So it looks like the survey doesn't come out till Sunday. So if you can spend like 5 minutes grilling me, that'd be great. I always want to try to improve. All right. So let's see. When you guys were doing this problem here, so if you're trying to find the gradient -2.5, what you need to do is use the partials, but then plug in that point at those partials. Okay? Plug in that point at those partials, where these were the partials that you found. Okay? So what did you guys get when you plug in the point -2.5? You get 6, and what is it, -4? Yeah, good. So then if I try to draw that vector, that means x is going to increase by 6 units. So 1, 2, 3, 4, 5, 6. And y is decreasing by 1, 2, 3, 4. Feels like slope, kind of. Okay? Does that look right? Somewhat-ish? So this is your vector right there. Okay? This is the gradient vector at that point. Okay? Did I do that right? 6 this way, 4 down. Yeah. Okay, and then your unit vector is still the same unit vector. So from here, x still is going to increase about 0.4 units, and y will increase about 0.9 units. So it's still this vector here. This is still u. Okay? This is, we never want to have you guys stand up. That would be like Cesar standing there, looking in that direction, and then Charlie over here, looking that same direction you. Those directions you look at are the same. Okay? Then you guys did the point -1, -1. So the same thing, you plug in -1, -1 into your partials, and what did you guys get? 4 positive 8. Okay, so you plug in -1, -1, and then you get 4 comma positive 8 though, right? Yeah, and so then that means that at this point, x is going to increase 1, 2, 3, 4, and y is going to increase 1, 2, 3, 4, 5, 6, 7, 8. So it goes like this. So that's this gradient. And the unit vector u is still the same, so it's still going to increase about 0.4 and then about 0.9, so it's going to be about 4.3. Okay? So notice that u is kind of pointing in the same direction as this gradient. Where here it was definitely not, and here it was hella not. Okay? So I just wanted you guys to practice knowing how to find a gradient vector, but I want to show you guys something. Question?
The terminal polynomial df -1 -1, I guess it's at 3, 3, 7.
3, 7, this vector?
No, that is okay. I mean the terminal point.
Oh, the terminal point. This terminal point. Yeah.
It's 3, 7.
It should be 3, 7. Let's see. 3. Yes, it should be 3, 7. Did I do it?
It's all 4.
1, 2, 3. It's because your angle. It's 3. It's right there. It's at 3. Yeah, it's just because where you're sitting, it probably looks a little off. Same. There is a reason why they all seem to intersect that way. Right, that's all right. Yeah, there is a reason. Something's going on there. Something's going on. What point do you guys feel like this? What point is around here? Remember, my drawing's not as good, but it was perfect. 1-ish and like 2, 3-ish, right? All right, let's take a look. So something's going on. Let's see what's going on. So this is the surface of that graph. Okay. Notice if I go to the point 1,3, I'm at its peak. I'm at its peak. But the question is like, why do the vectors, all the gradient vectors, seem to kind of point towards the peak of the function? Okay. So let me show you guys a set of vectors. You know how I just had you guys graph 3 vectors? So here, these are a bunch of different vectors. Okay, let me get rid of the surface. If I did that for a bunch of different points, this is the initial point, gradient. There's all these gradients for all those points. They seem to gravitate towards that point 1,3, which is where your surface is having that peak. Oh, I guess we can't see it from this angle. Yeah, so watch. Let me move this over here. So if I rotate it, notice that the gradient vectors seem to gravitate towards where the function has that maximal peak. Okay? And so what's going to end up, there's a reason that's going to happen, which I'm going to show you guys right now. This though will be very important in the next 2 sections, this concept of it gravitating towards that peak. Okay? So keep in mind that that's kind of what's happening. We're going to observe that there. But it's not an accident. It's not an accident. Okay, so why is that happening? What's going on? Let's take a look. Yes. Oh yeah. Go. So question, why do the gradient vectors seem to point towards the maximal point on the graph from what we were looking at? Why is that happening? And so let's look at the fact that we can write the directional derivative as a dot product. So notice that if I try to do the directional derivative at some point, we saw how that's the gradient vector at that point, dotted with u. Okay. On exam number 1, what was the theorem that used the angle between these 2 vectors? It was a theorem related to the dot product of 2 vectors and the angle between them. The cosine one, yeah. What did it say? This dot product should be equal to what? The magnitude of the gradient vector times the magnitude of the vector u times cosine theta, where theta here is the angle between the gradient vector and u. So it would be this bad boy here. This is the theta right there. This is the theta right here. And then this is the tiny theta right there. That's the thing. Okay? Angle between those 2. What's the magnitude of u? It's a unit vector, so the magnitude is 1. So what we have is a directional derivative at a particular point is just equal to the magnitude of the gradient vector times cosine theta. All right. So this is what I want you guys to discuss. At which angle will the directional derivative be maximal? All right. Is this ever going to be negative? No, right? So the only thing that can make it smaller, this will never change at this point. This will never change, right? This gradient vector at that point is just always that gradient vector. What can change though is my vector u, depending on how I rotated it. Remember I was rotating it earlier? So that, therefore, the angle between them can change. So when will this be the biggest? At theta being 0, because what's cosine of 0? That's where it's the biggest, right? When cosine is 1. So at theta being 0, if theta is 0, what does that tell you between the relationship of u and the gradient? They're pointing in the same direction, so what do we call that with vectors? They're parallel, okay? So therefore, u is parallel to the gradient vector at that point. Okay, so what? Okay. So that means, let's say I'm standing right here, and my gradient vector will be this vector. It doesn't change. This is the gradient vector for this guy. It doesn't change. But u, I can change it. What this is telling us is that when u points in the same direction as my gradient vector, that's when my directional derivative will be the biggest. What does that mean? That means that that's when my rate of change for z is the highest. What does that mean visually on the surface? What do you think? It's where you're going to hike, is the direction you hike to go the steepest, because you're trying to increase the fastest that you can. Okay? And so why are all these vectors pointing this way? Because here is the highest point, right above this. So walking towards it is going to be the steepest path going up. Okay? No.
Is this similar to when you take the first derivative and you set it equal to 0 to find the max points?
That's where we're going next class. Yeah, that'll kind of tie in again. Yeah. So let me write some of this stuff down because it's very important for your homework. So let's write it down. All right, remarks. No, I guess I'll write it here. So when theta is 0, that tells you that u and the gradient vector at that point are parallel, like what we just discussed. When theta is 0, what will be the directional derivative? What will it be equal to when theta is 0? The magnitude of the gradient vector, right? So we've actually discovered two things. That when u is parallel and points towards the gradient vector, that's the direction where you're going to increase z the fastest. The question now is, what is that rate? Well, when theta is 0, the rate will actually be the magnitude of the gradient. So the gradient is telling you two things: which direction makes you go the steepest, and the actual rate is its magnitude. Okay? So let's write that down. So the direction of the gradient at that point gives you the direction where z increases the fastest. Okay. And then the rate of that direction means that at that point, the rate is the magnitude of that gradient. It is the magnitude of that gradient vector. So let me make sure you erase this.
Is that when?
Say it again?
The when theta is.
Oh, when, sorry, when. When theta is it. So leave another bullet point here. Leave some space here in your notes. We're going to go back to that in a little bit. So here's something you'll see in the homework. For the function, we're still going to play with the same one. They'll say, which direction gives you max rate of change? And so what you will have to do, the direction that gives you max rate of change is the direction dictated by the gradient vector. Oh, shit. It has to tell you the point at 1, 1. So the direction is the gradient vector. So you figure out the gradient vector. You plug it into the partials. And so then, just like we did here, plug it into those partials, and we got the point, the vector 0, 4. That's the answer to this question when it says direction. It's asking you for a vector. What does that mean? That means if I'm at the point 1, 1, I need to walk this way, and that will guarantee that I'm going to increase z the fastest in that direction. Okay. The second question then says, okay, if that's the direction that gives you the maximal rate of change, find the max rate of change. To do that, we need a directional derivative. We need a directional derivative. What unit vector would you choose? Unit vector. Is this a unit vector? We know we want to walk that way, but we need to make it a unit vector, right?
0, 1.
So notice that if I do u to be this vector, and I divide it by its magnitude, what's the magnitude of that? 4. So that just gives you the point 0, 1, right? So if you find the directional derivative at that point, I'm going to show you this 2 ways. Plug it into the partials again. This is my A, this is my B, just like how you guys did earlier. This is just 0. This is just a big fat 0. And then this is partial of that is going to be 4. So what's my maximal rate of change? 4. In the direction of the gradient vector. But this is what I'm trying to say by the second bullet point. You don't have to do all that. You could just literally take the magnitude of the gradient vector. Because what's the magnitude of the gradient vector? 4. That is the maximal rate of change. So notice that this is just the magnitude of the gradient vector at that point, though, at that point. So this gradient is telling me two things. One, I need to walk this way to guarantee z will increase the fastest, and the rate at which it'll increase the fastest is 4. Okay? If you guys look at the 2 example problems you did before the break, where you used this function, where you were going from P to Q and from P to R, what was the rate when you went from P to Q? Look at your notes. In the previous example, when we went from P to Q and I had you find the directional derivative, I think z was negative. It was negative 2.8. So z is not even increasing, right? What about when you went from 2 to R? Sorry, P to R. It was like 3.6. But look, this one's even faster. Z is increasing at a rate of 4 units, not 3.6. So this one beats it, because that is the one that gives you maximum rate. Questions? All right, I'm gonna have you guys do a 5-minute summary of what we just did, because your eyes show me that you need a little conversation. So real quick, try to just discuss with your classmate what this is telling you. Okay, do a little summary real quick. I have my water bottle in my eyes. Do a quick summary, guys. Quick summary.
The first part. Oh, yeah.
Oh, like this? So you answer this question with a rap? Yeah.
Correct. So for this chapter, anything about direction has to do with a vector. Like which way are you supposed to be walking? Which way do you go? And to describe that, we have to use a vector, because a vector has a direction ingrained in it.
Oh, okay.
Yeah.
The second one doesn't say this formula is correct.
I kind of thought that the second bullet was like. Which I guess would happen because data 0.
All right, guys, let's see. Let's say this was your homework problem, number 21. Okay, let's say that was your homework problem. And the question says, let me share my screen, hold on. It says, find the maximal rate, where the hell is find the maximal rate of change of f at the given point in the direction at which it occurs, okay? This one's only asking you to find the maximum rate of change, okay? Versus, let me see if there's another question that says, no. Hold on, I want to see if there's one that asks you for the direction. Okay, I can't find it. It's okay. But what is the direction? So this is a function. It has a funky surface, and you're at the point 4, 1. How would you find the direction that gives you maximal rate of change. What would you have to do? Find the gradient. But how do you find the gradient? What do you need to do? How do you use that function to find the gradient? Take the partials, f of partial x, partial y, and then what do you do with that? Well, what do you do with this point first, with those partials? Plug it into the partials, then it gives you your partial of x at that point, your partial y at that point, and then that's the vector. That is the gradient vector. And then how do you answer this question? What is the maximum rate of change? Take the magnitude of the gradient, and that answers the question. Okay? That's a different question compared to these ones. It says, find the directional derivative of a function at a given point in the direction of a vector v. Okay? See how this one's not asking anything about maximal rate of change? It's just saying, find the rate of change, the directional derivative. So let's say you have to do this problem here. It gives you a function, it gives you a point, and it gives you the vector. So you have to take the directional derivative. That's what you did at the beginning of class. You need a unit vector. Is that a unit vector? No. So you normalize it and make it a unit vector. You take the partials. You use a theorem to find the directional derivative, which I erased. You're gonna end up, to find that bad boy, you're gonna need to do this. Yeah, the theorem that we discussed there. Right? So you find your unit vector, so you find your A, your B, you find your partials, plug in the points in the partials. I mean, you can, if you want to write it like that, that's fine too. You can even say, find the gradient and dot it with your unit vector. I think that's even faster to say. Find the gradient and dot it with the unit vector. That will give you the rate of change towards u, or sorry, towards v, which is the same as u because u is just the normal vector. Kind of see how it's a little bit separate? It's all going to sound the same. That's why this section's hard. But you have to see the difference between the questions. Okay. I hope that clarified a little bit. All right. All right, the last remark I wanted to make. Let's go back to this bad boy here. When will this be? When will you have this be the minimum, I guess? Not the minimum. This is directional derivative, right? We saw that when theta is 0, the directional derivative is the largest, is the most positive. There you go, it's the most positive. When will it be the most negative? When theta is pi, right? So if theta is pi, what would be the relationship between u and the gradient? They're parallel, but in the opposite direction. That is the opposite of this. That's going to tell you when your function is going to decrease the fastest, if you walk in the opposite direction. Okay, so that's the last thing I'm going to write here. So it says the direction of the negative of the gradient vector gives you the rate at which z decreases the fastest. Decreases. That you need it to be negative. The opposite direction vector. That's the last remark. So if you go towards the gradient, you increase the fastest, but if you go completely opposite of the gradient, that's where you go, you're going to go decrease the fastest. Okay, almost done, guys. We're almost done. The last part that I want to talk about has to do with these pictures down here. Has to do with those pictures. So the last part, we're going to call it the gradient and level curve. Let me remind you what a level curve was. So consider the level curves of some function f. Some function f. Let's just draw a little picture. And you have some level curves, and then remind you what a level curve is supposed to be. Remember that the level curve says that all the points that you plug in into your function that are on that curve will output a specific z value. Let's say this is k equals 10. Let's say this is k equals 20. Let's say this is k equals 30. That means that all the points on this level curve here, you plug them into the function, and what will they output? All the points on this level curve will output what? Z equals 10. What does that mean? You have to do that in one of your home problems. That means that the level curve is on the xy plane, but if you levitate it at a value of z equals 10, that's that level curve corresponding to the surface. All the points here will output what? 20, and all the points here will output 30. So remember, we're calling this a contour map, kind of like when you're hiking. If I hike along this part of the trail, I stay at 10 feet, let's say, 10 meters or whatever. If I hike around here, now I'm going to stay at 20 meters, and so on. You guys remember that? We're doing that in the beginning of the chapter? Okay, so now we're going to take it up a notch. I'm standing right here at this point, and I want to increase my z the fastest, which is my gradient vector, right? But how would I draw that so that I can increase the fastest? Will the vector point like this way, that way, this way? Like, how do you think I should draw that vector? Towards the 20 line, right? Because I want to imagine you're like at 10 feet on the trail, and up there's 20 feet. I want the shortest path possible to get up there. Take it.
Can you just like maintain the same? Just thinking, like maybe something with
What do you mean by normal?
that's not normal, but like, is there like some way to get that angle?
I think the next part will answer your question. If you're here, which way should it point? Towards the 20, right? So that it goes there the fastest. I want to hike up. I want to go up here the fastest I can. Okay, and this is the part I think is going to answer your question. Notice that if you draw a tangent line at that point, what's the relationship between the tangent line and that vector equation? It's going to be perpendicular to it. If I draw a tangent line here, it's going to be perpendicular there. Okay? So what your textbook's going to say is it's going to say, and these are all little gradient vectors depending on the point that I'm picking. Those are all gradient vectors. So what your textbook's going to say is that your gradient vector is perpendicular to your level curve. What does that mean? If you draw a tangent line, it's perpendicular to the tangent. So if I want to increase the fastest, which is my gradient, I have to make sure I go perpendicular to the level curve of that. So let's work some of this stuff out. So since the gradient points in the direction of max rate of change, we end up having that for any point x naught, y naught, sorry, I'm bringing back the knots again. In the domain of F, the gradient vector at that point is perpendicular to the level curve containing that point, containing x naught y. And then I wanted to include some graphics, which are on the bottom part of your paper. Right. So so if you have some level curve here, you're on this level curve, and that point is on the level curve, then your gradient is going to be orthogonal, or sorry, perpendicular to the level curve. And here's like a little contour map of a trail. So I want to always go perpendicularly to that level curve to make sure I'm increasing the fastest. And then here, you have all these little gradient vectors. And what I want you guys to notice is they cross the level curves perpendicularly, depending on the level curve. Okay? So remember when we were looking at this picture here? Okay. If I was asked to draw a the level curves, well, it has to be perpendicular here. So notice that if I do that, it's like I have like this round shape to make sure that my level curves are going to be perpendicular to my gradient vectors, right? And so my level curves are going to be like these circles, which makes sense because those circles are the level curves of my surface. They're circles at different heights for z. So it's matching, okay? So exciting. We're like connecting so many different concepts in the class, which is also a little scary. Yeah, totally. Yeah, exactly. So that's what we're going to look at. So let's say right here there's a peak, and I don't know, somewhere in the corner over there is another peak. If you are a point that's closer to this peak, you're going to gravitate towards that peak. But if you're a point over there that's closer to that peak, you're going to gravitate towards that peak. If you're somewhere in the middle, that's what we're going to talk about on Thursday. There's like this funky thing happening that you're like, which way do I go? And it turns out you'll go nowhere. You get stuck. Okay, so we'll talk about that. Yeah, we'll talk about that. Yeah, good question. That's part of the next section. Thinking ahead, like. All right, it ends with a doozy. Looking out for you guys. Okay. So if gradient vectors are perpendicular to level curves for a function of two variables, we're going to do everything we just discussed and extend it to a function of three variables. Okay? We're going to do it. So all of this extends to functions of three variables. Where let's say you plug in x, y, z, and you get some fourth dimensional coordinate. So the gradient is still similar to what we did. So the gradient is still going to be a vector, but now how many variables are you inputting? 3. So how many partials do you have? 3. So now it's going to be f partial of x. Here, just to save time, let's just write f partial of x, f partial of y, and f partial of z. So now it has 3 components. Okay? For this whole part we're going to write, I want you guys to think of these 3-dimensional points like literally right now in the classroom. There's a point right here. Let's think of it as a hummingbird. You know how hummingbirds can like stay in place? There's a hummingbird right here floating, okay, at this point. The location of the hummingbird, you plug it into some function, and let's just pretend, to make sense of all this, that W is the temperature of where the hummingbird's at. So if the hummingbird's over here and the temperature is pretty cold, then it has a small value. But if now the hummingbird's over here and you plug in its 3-dimensional point, and let's say it's warmer, then now W is bigger. You guys kind of cross that a little bit. It's a little hard, okay? So what does it mean to do a directional derivative then? So the directional derivative towards the unit vector u, which now will have 3 components, we still use the same property that we did. So to find that directional derivative, I still can do the gradient vector and dot it with u. I can still do it that way. I dot this vector with this vector, and that'll give me my directional derivative. What does that mean? There's my hummingbird floating right here. And u is telling it which way to fly. So if it flies this way, if it flies that way, that's going to tell me how the temperature is changing as it flies this way. But if it flies this way, it'll tell me how the temperature is changing as it goes in this way. You guys kind of get a sense of that? That's kind of what this is doing. Again, it's abstract, but let's say W is temperature. It's giving you the rate of change of how W changes with respect to the direction of U. So I'm thinking of W as temperature. So I'm saying the rate of how the temperature changes as the hummingbird flies this way, if it's standing right here at the point X, Y, Z. Versus if it's over here and it's still the same direction, the temperature may change in a different way here as it changed here. You guys kind of see that? Okay. My hummingbird's here. Now I want to say which way should it fly so that it increases its temperature the fastest. And it's still this bad boy. It's still the gradient. So you plug in that point into these partials, and it'll give you some 3-dimensional point that is where the temperature will increase the fastest. That might be, let's say there's a big ass heater at that little like mechanical thing though, right? And the room's pretty cold in the bottom. So the hummingbird's going to want to fly that way to increase its temperature the fastest. So the gradient would be there, versus over here, the hummingbird would have a gradient that points that way so that the temperature increases the fastest that way. What? Kind of trying to give you guys an example to see how what makes sense of this. So let's write that out. So so there is a max rate of change in the direction of the gradient vector still at a particular point, and the max rate is again still just the magnitude of that gradient. I'll leave this. Okay. So these are the three things we've discussed so far, right? But now in a three variable function. Does a three variable function have level curves? Or does it have level surfaces? Does it have level surfaces? Okay, almost done, I promise. It's a surface so that every point on that surface has the same temperature. And there's another level surface where every point on that other surface has the same temperature. So it's a bunch of level surfaces. Okay? Oh, I'm a little nervous, but here we go. The next part goes a little higher end mathematically. But you guys are badasses, I'm sure we'll work on this together. So the gradient vector XYZ. Do you guys see this picture at the very bottom with the little ellipsoid? Okay. Pretend that ellipsoid is a level surface. Okay? Of a function of three variables. Just the way the gradient is perpendicular to a level curve, in 3D, a three-dimensional gradient is going to be perpendicular to a level surface. So what we're going to do is, remember we were doing equations of tangent planes? Okay, for functions? We needed to find a normal vector. That gradient is going to be a normal vector to a tangent plane, because it'll be perpendicular to the surface. Okay, but let me write that part out. Is a useful tool for finding normal vectors of tangent planes. And let me show you how we're going to do this, and then we'll be done. We're done with this section. So consider a function of two variables. Z equals f of xy, like that. In section 14.4, I had you guys find tangent planes to functions, surfaces of functions like this, okay? And point A, B, f of AB on the surface of F. Here's where we're going to use a three variable function to somehow apply a tangent plane, okay? We're going to define a new function. We're going to call it capital F that has three variables, x, y, z. And what we're going to have it do is we're going to have it be this z minusing the function. Okay? Then the level surface k equals f of xy, which means the level surface that contains all the three-dimensional points that output k, okay, where k is equal to 0 is the surface of, so it's a level surface where this new function that we define is equal to 0. So it's this bad boy that equals to 0. Okay, I'm gonna stop. So this is a surface where, let's pretend all the points on this surface have temperature 0. Let's just pretend we're using temperature. Okay? This function we defined it to be this way. We're doing a little trick here, okay? We're defining a new function strategically so that it's literally z minus z. Okay? So then this thing is that means this thing is equal to 0, since that's how we defined our function. But notice this, I can move the f of x over here. And so the level surface of this new three-dimensional function is really just the surface of my function of two variables. The level surface of this bad boy is the graph of little f that contains this point. Okay? It's gnarly. And so since we know the gradient of this function is going to be perpendicular to the level surface, right? Since the gradient of capital F at the point AB, f of AB, is perpendicular to the level surface 0 f of x, y, z, that means, and since the level surface is just the graph of f, that means that this gradient vector at that point is perpendicular to the surface, which is the graph of f, because they're the same thing. The level surface of this bad boy is really just the graph of the function. And so this gradient vector is the normal vector to the tangent plane at that point. So let me end with an example so you guys have one to refer in your notes. It's a doozy, I know that. But let me give you an example. Let's say we want to find the equation of the tangent plane of, let's say the function is just xy. We do x squared y at the point 1, 1, 2. F of 1, 2. Okay? This is what you did in section 14.4, the homework that you guys, I think, turned in, or maybe you're turning in. Okay? What this is saying is you could do what you did in section 14.4. That's fine. You could do what you did there. But this is giving you an alternative tool here. Let me plug in 1, 2 into the function. So that's 1 squared times 2, that's just 2. That tells me the point of my tangent plane. Is that? Yeah. How do I find the normal vector now? The normal vector of my tangent plane. I'm going to copy what I did there. I'm going to let capital F of x, y, z be z minus my function x squared y. Minus my function. If I take the gradient of it, That's the partial of f with respect to x, partial of y with respect to y, oh, sorry, of capital F, and with respect to z, actually, let me write it like this. Just the way it looks like that. So help me out here. What would be the partial derivative with respect to x here? What is the partial with respect to x of that guy? This one? It's just the partial of x, right? Right? Let's do it with respect to y of capital F. 0 minus partial y. And then let's do it with respect to z. 1. Are there any z's here? No, it's a big ass constant, right? So it's just going to be 1. So then take the partial of f with respect to x. It's 2xy. Take the partial with respect to y. Negative x squared and then 1. So now plug in the point 1, 2, 2 to give you the normal vector. This is the normal vector of the tangent point. So you plug in 1 and 2, what's that, negative 4? Negative 1 and 1. And so then you use this normal and you use that point, and then it gives you the equation of the tangent. So this is the normal, this is the point. And so then the equation is going to be negative 4 x minus the x coordinate of the point, the y component, y minus the y component of the point, plus c here, which is 1, z minus the z component of the point, 0, and then you can simplify it if you want. That would be your equation of yours. Sorry guys for ending like that, but I don't want it to get, it's deep, so I want to be able to explain it. All right, we're done. Shit, I'm 3 minutes over. We're done, guys. I'll stay if you have questions.